Okay. So this graph below is a graph that represents this system. Now, we're not used to seeing our straight lines in this form. This is called the AX plus BY equals a constant form. We're used to seeing them Y equals. We're used to seeing them in the slope-intercept form. Well, you could, just so that you can see something about these lines, you could in your own either mind, if you're capable of doing that, or scratch it out on the side of your paper. You can solve that first equation for y by subtracting x from both sides and then dividing by 2. So this is the form you're more used to seeing a straight line. Y equals the slope times x minus a constant. So if you look at this, this tells you that you go through 0, 1, your y-intercept is always the constant, and then here's your slope, minus 1/2. So that has to be the blue line because this has a negative slope. Notice this is the equation for the blue line. It's just in what we call a general form versus the slope-intercept. They're the same thing. This particular one, if we were to look at it, if I did a little, subtracted 6 from both sides and added 2y to both sides, and then divided by 2, I'd get 1/2 x minus 3 equals y. Notice this one has the same slope, but it's going in the other direction. So that's the red line. Okay. So when you look at two linear equations at the same time, you can actually look at 3, 4, 5. But if the number of equations you have can have up to that many variables, okay? But if you have 2 variables, then you can graph it on a 2-dimensional plane. So if we're trying to find the solution to this equation, there's an algebraic way of doing it, and this is the graphical way of doing it. We looked at this the other day. So what does this intersection point tell us about these two equations? What does that intersection point tell us? Or what do we call that intersection point other than intersection point? What does 4,1? How does 4,1 relate to each of these equations? It solves them. Well, every point, I'm just going to be a little picky, Alan, if you don't mind. Every point on this blue line solves this equation, and every single point on this red line. Yeah, it's the one point that lies on both of the lines because it's where they intersect. So what does that mean? It means if you go back to this equation, and you put 4 in for x, so let's do that with green. Everywhere you see an x, you're going to put a 4. And you put 1 in for y, and we'll do that with blue. Oops, it's supposed to be blue. Then we should get 2 for the first equation. Did I write that right? Oh, it's -1. Thank you. -1. I knew I made a mistake because I knew that didn't add to 2. So 4 take away 2 is 2. That checks. And 4 -1 is 4 plus 2, which is 6. That checks. So since it is a solution to both of those equations, you know something. You know if you were to graph this, that would be the place they intersect. So when you do the algebra and solve these systems, or when you solve these story opportunities and you get the answer, you should imagine that that's a point of intersection if you were asked to graph the equations. One is a visual. 4 -1 here is a visual solution to both equations. And what we're going to see in a minute is algebraically, how do we take something like this and get this answer? But I wanted you to see the visual for this. Any questions on what 4 -1 represents? Does anybody remember how you found the answer to a system? If you haven't looked ahead in the lecture notes, anybody were you able to dust off the cobwebs and remember anything from algebra about solving this, Coleman? There's a Okay, you're right. There's 2 algebraic ways to do it. Okay. And the reason why we rely on algebra is, even though this one could be easily solved with a visual picture, sometimes we could get a really nasty solution like 17/9 for x and -3/7 for y, and you're not going to be able to easily pick that up from a graph. Okay, so we have these two algebraic methods. One's called substitution. Your book calls the second one addition, but that's the one that Coleman was referring to as elimination. Both of these terms are used for this method. Your book picks the one addition. I have always referred to it as elimination, so I'm going to have to kind of use both terms interchangeably just to help remind myself to say addition. So let's take a look at the idea behind each one. And this should be a review. This is prerequisite material. So here's two straight lines. Again, if you were looking at this, you know they're straight lines because you don't see any powers like 2 or 3 or anything like that for exponents. Everything has the highest exponent is 1. And if you were asked to solve this, if I were given this equation, this system, excuse me, if I were given this system, I would use one of those methods versus the other. I would do this with substitution. And the reason I would use substitution is I see a 1 right here in front of this y, which makes this equation really easy. I can rewrite this equation so it says y equals something very quickly. What would it be? Y equals what? If I solve this equation for y, solve for y, I would subtract 2x from both sides. And now I have a new name for y. Well, actually, it's just had a little plastic surgery. It's the same equation. Now I can say, wow, I know what to call y in terms of x. So the idea here is that you have rewritten y in terms of x. Okay, you've rewritten y in terms of x. So now you use this idea of substituting. Okay. So you take your other equation, which is just one equation with two unknowns, which has an infinite number of solutions. There's an infinite number of ordered pairs that makes this true. But we're trying to find the one, if possible. This may not even have a solution. We're just trying to find that one intersection point. So we use one of the equations to solve for either x or y. We chose y here because it had a 1 there. It was nice and easy, no fractions or anything. And now we're going to take this and we're going to replace the y we see right here with what it's equivalent to. So this becomes 3x plus 2 times, and now I throw in what y is equal to. It's alter ego here, 1 minus 2x. And now I have an equation with one variable. I can solve this no problem. Okay, so let's go ahead and do it. 3x plus 2 minus 4x equals 4, minus 1x equals 2, x equals -2. And what students do now is they're so used to solving equations for x, they stop. And what's the problem with that? You have to solve for y, right? Is that what you're going to say, Karen? Yeah. You're looking for, remember, anytime you solve an in system, in this particular case, you're looking for an ordered pair. You're looking for an intersection point. So once you find what x is, you still have to find the value of y. Now here's where you got to be careful. Never use any of the equations you've rewritten, because if you made a little mistake, your mistake will sort of reinforce itself. Always go back to one of the equations. And if you're really tenacious, you'll check both. But all you have to do is check one. So let's go back to the second equation here, which is 2x plus y equals 1. And where I see x, I'm going to replace it with a -2. And then I'm going to solve this for y. So this is -4 plus y is 1. Y equals 5. -2, 5 is the solution to the system. And it's also the intersection point of these two lines. And if you quickly put the -2 in for x up here, you get a -6. And if you put the 5 in for y here, you get a 10. and negative 6 plus 10 is 4. So now you can really be very confident that you've done everything correctly. Any questions at all about the idea of substitution in order to solve this type of system? Anything at all? Okay, so again, yep, Karen? No, you'll always have your choice, okay? So that's why I'm showing you both. So even though I would use substitution here, some people really like the addition method, or what we said was called the elimination method. I have no particular favorite. It's just that sometimes one method is more efficient than another, is quicker, that's all. So let's take a look at how we would do this. Someone want to read me the system again? I've 2x plus what? 3x plus 2y is what? Thank you. Okay. So what the elimination or the addition method says is, what happens if you add both sides? So let's just see right now if we add both sides together like this. So if we were to add both sides, I'd get 3x plus 2x on this side is 5x. 2y plus 1y is 3y. That equals 5. That doesn't help me at all, because now I have one equation with two unknowns, so no help. Although this idea of adding both sides can be helpful in the situation where you get rid of one of those variables. Because what is it that we want to end up with? We want to end up with one equation with one unknown, just like we did up here. After I substituted, I got one equation with one unknown. So this is just another way to do it. So this doesn't help, no help. Okay. However, we know because we have equations that we can multiply both sides of an equation by any number that's not 0 without changing it. So the idea now is to say, if I want to eliminate x or y, if I can make the numbers that multiply, which we call coefficients, opposites, I know when I add opposites, I get 0. So I always look for the easy way out. If I can get away with just multiplying one of the equations versus having to multiply both of them, that's the route I take. So you always look for this 1 in front of one of these variables, because if you make that say negative 2y instead of 1y, when you add them up, you're going to get a 0. So you can do that by multiplying both sides of this equation right here, everything on both sides, by negative 2. So I'm going to take a minute to rewrite my first equation all over. And now I'm going to write my new equivalent equation to the second one. That's going to be negative 4x when I multiply everything by 2 minus 2y equals a negative 2. Now I'm going to try this addition on both sides, and hopefully I wind up with one variable. That's exactly what we're doing. Okay, so when I add 3x plus a negative 4x, I get negative 1x. And this is why we chose the negative 2 dies, is so that these two, when I add them, become a nice big fat 0. Equals 2x equals negative 2. It's the same thing we got with the elimination method. And now you go on and you find y equals 5. Same way we did before. Okay, so this idea of solving an equation with two unknowns is an important idea, so you can solve the story opportunity that you were just working on with the interest, with the bonds and stocks, if you choose to do it with two variables. So let's go back to that problem and take a look at it. A lot of you have made success, have found your way to this answer, but I want to show you the two approaches. And you take the approach that works best for you. I'm just going to set it up. I'm not going to finish it. If you were using one variable to do this problem versus two, let's see what approach you would have. Both of them get you to the exact same place. It's just a different way to think about it. This first sentence is critical in terms of setting up your unknown, either one unknown or two unknowns, because it tells you the total. Anytime you're given a total, that should go Beep, beep, beep. That's an equation. That's a what equals a what. Beep, beep, beep. So what's equal to $5,000? Just in words, no algebra. What's equal to $5,000? The amount invested in stocks. So that's one way to start off, is just get a sense of what you're doing in words. The amount invested in dollars in bonds and the amount invested in stocks is equal to $5,000. That's your first what equals what. And that's the only what equals what you may need to do right now, okay, just to get a sense of what's going on in the problem. Now, if you assign two variables to this, say an x and a y, that would be a line that would have an infinite number of solutions. So you wouldn't get anywhere. You're interested in a particular amount that you invested in stocks and bonds that then has the next piece that would give you a certain amount of interest, okay, based on the fact that the first one earns 5% and the second one earns 8%. So if we're using one variable, I'm going to assign x to be the amount that I invested in bonds. I could call it a B if I wanted. I could call it a smiley face. It doesn't matter. Okay, so I'm not going to shortcut this. I'm going to write it out. X is the amount of money invested in bonds. Now, this is the difference between one variable and two. How do I represent, in terms of X, the amount of money invested in stocks? Using X, not a brand new letter. So if I knew this amount right here, and then this is what I always tell students. Pretend this is a number if you can't work with the variable yet. Pretend that this is $3,000. If this was $3,000, how much would this be? 5,000 minus 3,000. That's what your brain does, and it would say 2,000. So if you're working with one variable, this is the key. You always use your total. And you subtract from your total the part you know, which is called X. Notice the total has to come first or you'd end up with a negative number. So this is the amount, and this is where you get to use your little, what do you call those things? What do you call these little lines when you're copying what's right above it? Dittos, okay. Invested, sounds like a cartoon character, in stocks, right? That's how you do it with one variable. How do you do it with two? You say the same thing, but you do this. You say X is the amount in bonds, blah, 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 and Y is the amount in stocks, okay? Blah, blah, blah. That's the only difference at the beginning. Right? Now, when you're doing two variables, you have to represent that first phrase equation we did here. The amount invested in both is 5,000. That's how you get your very first equation in your system. We've got to come up with another equation. So you got two things going on here. The total amount of money you've invested and the total amount of interest. So if you're working with just one variable, you would say 0.05 times X is the amount of interest in dollars earned on X dollars invested in bonds. And 0.08 times 5,000 minus X is the amount of interest earned on Y dollars in stocks. And now, if you're working with one variable, you add these two together and you get $295 and you're all done because you have just one variable. All you do now is solve this for X. So some people really like one variable because they get their one equation, they don't have to think about any other method, and that's it. You go from there. However, if you like this idea of two variables, then you're going to end up with exactly the same equation. You just get there a little differently. Again, the same idea, 0.05x plus 0.08, but now instead of calling it 5,000 minus x, you're calling it y, is equal to 295. So this is your system that needs to be solved. Okay? So to solve this system, anytime you have an x plus a y, it's much quicker to solve this first equation for either x or y and use substitution. So this looks just like the one we did with two variables. I'm going to take this equation and solve it for y, which is 5,000 minus x. Lo and behold, it looks just like this one does now. Same exact thing. And where I see y in the second equation, I'm going to substitute in the 5,000 minus x. And I get exactly the same result. I just got there a little differently. Okay? So this is really a personal preference. I know some of you like the two variables, some of you might like the one. It doesn't matter which you do. Okay, you get to the same result. I'm just curious, how many people prefer one variable? 1, 2, you're in the middle, 3, 2? Depends on the problem. Like, what makes a difference for you, Andre? Yep. Okay. You like two? Someone say something about two variables? Yeah. Sometimes the wording, because most of us don't think about, I think that the 5,000 minus x it's a method that we particularly learn in our 096 class where you take the total and you subtract the thing, you know. It does feel a little forced to some people that normally their first impulse is to say x is one and y is the other. Okay, so I want to move along to our class for today, which does this again. And you should be pretty much set now. This is the same problem, exactly the same problem, except the story is different. Instead of talking about interest and putting money in stocks and bonds, we're talking about scholarships and where we invest it. So some people really like using these little charts here. So the amount invested, they might say X and Y, the percentage and all that. If this table helps you, use it. Otherwise, you should be able to do this problem. I'd like you to try this with two variables though, okay, because that's the section we're on. So try this at your seats. I'll help you if you need it. And we'll talk about it in about 5 or 6 minutes. I think everybody successfully got through the scholarship problem. Again, what the table does, once you label the table right here, when you label the table, you're basically defining your variables. So that, for those of you who feel a little like, oh, I don't like writing that out, if you just put in the column names and the row names, then you've defined your variables when you put it in there. And what's really nice is when you do something like this, it gives you a really nice structure for coming up with your two equations. Because if you're given totals, which these problems often will do, you're given a total amount invested, so you can put the 10,000 right here. And when you add up those two things, voila, there's your first equation. X plus Y is 10,000. When you multiply across each row, you get this thing, the amount of interest. These should have little dollars here, by the way. So 0.04x is the amount of interest you'd earn at the lower rate, and 0.08y is the amount of interest you'd earn at the higher rate on Y dollars. This is the amount of interest you earn at the lower rate, which is 0.04 on X dollars, because that's what you've invested in each of those. Then guess what? When you add straight down, you're going to get the other total that they give you, the 550. And voila, there's your second equation. So some students really like these little tables because it gives them a little bit of structure to help them set up their system. And from here you solve. And what did you get? You got the lower rate was what? 6,750 and 250, thank you. And here was what, 37? Right, okay. All right, so one other type of problem I want to talk to you about in this section, which is really one of the big applications, and a lot of you are in the BAT program, I know, and you've got to take economics, or you've already taken economics. No? Yeah, how many are in the BAT or a business program here? Just 4 people? 5. Really? Oh, okay. Well, we usually get a little more. But in economics, you deal, or in any kind of situation, this intersection point can actually have a meaning. And in business, it's called the break-even point. Or in economics, it's a point where your two dependent variables are equal. So a lot of times we want to know, if I invest this amount of money in a company and then I sell a certain item, I take in money. And for a while, I might not make any profit because I've put out more money than I'm actually getting in. But at some point, I'm going to have the same amount of money going out as coming in. And then everything after that is golden. It's what we call profit. So if we have the following situation, which is, if you want to just, kind of chill out, this is in your textbook. It's a problem that deals with creating new wheelchairs. And it says the company plans to invest to manufacture these radically different wheelchairs. The fixed cost, so before they start even producing this, the startup cost is $500,000. That's the fixed cost. And then it's going to cost $4,000 to produce each wheelchair. So if I wanted to create what's called a cost equation, let's call that C, I need to define my cost in terms of the number of wheelchairs I produce. So X has to be the number of wheelchairs. X is not wheelchairs. It is not a qualitative term. It's a quantitative term. It's a number. So someone want to help me create what would the cost equation look like based on this sentence right here. Fixed cost will be $500,000 and it will cost $4,000 to produce each wheelchair. Yep, Trevor? Plus 4,000 times X. Right. What's the slope of this line? 4,000. And what's the y-intercept? 500,000. When I sell no wheelchairs, it's still costing me 500,000. We're so used to having our straight lines with the slope term first, slope times X, but really, in real life, we think about, what do we start out with? What is our starting amount? Right? Now, how do I figure out my revenue? My revenue, huh? Okay. Yeah, because they've got a lot. Now they're going to sell each. I wonder if that's right. Does anybody have a book with them? I wonder if it should be 6,000. No, I think it's probably 6. Does anybody have their book? Turn to. It said 400. Okay, thank you. All right. Okay, so Morgan did the problem in the book. It was 400. I'm going to take her word. I have a typo there. I think when I did this last semester, it took a long time before they broke even, and I forgot to change it. Okay, so the revenue is the amount that they take in for each wheelchair times the number of wheelchairs they produce. So they take in $600 per wheelchair times the number of wheelchairs will just give you my dollars. So if I were to graph this with my graphing calculator, I would do something like this. I would put my revenue cost in for Y1. And this is where, you got to play around with the window clearly. Y1 would be 500,000 plus 400x, and that's my cost, and my revenue would be 600x. And clearly, I can't do the standard window from -10 to 10 and 10 to 10 because my y-axis is starting at 500,000. So my window for my y minimum, I would probably put at like 490,000. I'd probably start it there. My maximum, I don't really know. I'm going to put 2 million in. I don't really know the answer here. Let's see, do I need one more? I don't have glasses, okay. My X max is 0. I don't know how many wheelchairs I have to sell. I'm going to say 1,000. And then I'm going to just graph this to see if I can find my intersection point. And if not, I definitely have to adjust my window. So my X needs to be bigger. So I'm going to say 20,000. That should do it. Let the calculator do all the work. Woo! Woo! All right. Now, second calc, where do they intersect? This is the part I like. Enter, enter, enter. And that's the answer I should get when I do this equation algebraically, that they have to produce 2,500 and sell 2,500 in order to break even. And this says the money going out, how much money is that? A crap load, 1,500,000. And the money coming in would be equal, 1,500,000, because that's the point where they're equal. So how would you find the X that makes these two things equal? Well, you set them equal. You say, when does C equal R? And then you put in your two equations for each side. And you solve that single equation with one unknown. And to do that, you subtract 400 from each side. Did I do everything right so far? Okay. What? Well, Morgan told me I made a typo and it should be 400 up here. I know it says 4,000. Do you see this little cross out here? Okay. You might have been talking when I went over that, Andre. Okay, so if we divide both sides by 200, what do we get when we divide 500,000 by 200? What do we get? 2,500. Okay, that just gives you one part of that point. That gives you how many wheelchairs you'd have to sell. And if you put X back here in either of these equations, you'll find out that the money they take in and the money they put out is equal. It's 1,500,000, which is what we got when we found the intersection point. Okay, I'll see you on Friday. We have our first quiz on Friday. Have a good day.